Good evening, students. So far we have been discussing differential equations, and we discussed earlier in the video lectures on second order differential equation, then some series solutions, especially we learnt Hermite differential equations, under which we learnt Hermite polynomials, generating functions, orthogonality properties, recurrence relation of Hermite differential equations, all those things we discussed. And also next power series we discussed on Legendre differential equations, and out of which we have learnt Legendre polynomials, generating functions of Legendre polynomials, Rodrigue's formula, orthogonal properties of Legendre polynomials we discussed. And in the syllabus it has been given as Sturm-Liouville theory at the beginning and at the end. So now we are going to club together. We are going to learn Sturm-Liouville's theory first in one video lecture, and subsequently it is followed by Green's function. So we are going to learn in the next video lecture Green's function, and we are going to combine these together, that is Sturm-Liouville's type equation in one dimension and their Green function we are going to learn. So we have three lectures. One is Sturm-Liouville's theory, then another one is Green's function, followed by Sturm-Liouville's differential operator on Green's function, which is nothing but Dirac delta function, and we are going to learn all those things. So in this video lecture we are going to learn Sturm-Liouville's theory, and in fact we know Sturm and Liouville, there are two different mathematicians, and one was from Switzerland, then another one hailed from France. So two different countries, two different mathematicians, Jacques Sturm and Joseph Liouville, both lived around 18th century. They introduced second order differential equations under appropriate boundary conditions, and of course we can have some solutions which are nothing but complete solutions. Complete means we can have in terms of power series, and also those solutions are orthogonal sets. And these differential equations which we are going to study, Sturm-Liouville's theory, it arises directly as mathematical models of motion according to Newton's laws. In fact, in addition to that, we can say that this method can be used as a separation of variables to solve so many problems in physics, especially classical partial differential equations of physics such as Laplace equation, heat equation and wave equation, and so on. So now we will go straight away into Sturm-Liouville's theory. Sturm-Liouville's theory, this is the differential equation. So equation 1 is the Sturm-Liouville's theorem, and of course, as I said in the introduction, that we will have to have boundary conditions. So it's a homogeneous equation because right hand side is equal to 0. So we are going to consider this type of differential equation, which is nothing but Sturm-Liouville's theorem. Here d by dx of p of x dy by dx plus q of x plus lambda r of x times y equals 0. And of course p of x, q of x, r of x, they are all functions of x, and p has a continuous derivative we can differentiate, and q and r are continuous function, and p of x and r of x are greater than 0 for all x which belongs to a and b. A and b are boundaries. A is one boundary and b is another boundary, and lambda is a parameter which is independent of x. Two boundary conditions that we are going to apply. So according to equation 2, a1 times y1 y of a plus a2 times y dash of a, which is equal to 0. So y dash of a implies that dy by dx, and b1 y of b plus b2 y dash of b, which is equal to 0. So these two boundary conditions that we are going to apply, and of course a1 a2 b1 b2 are real constants, and a1 a2 are not both 0. Similarly, b1 b2 are not both 0. a1 can be 0. Suppose if a1 is 0, a2 should not be equal to 0. if B1 is 0, B2 should not be equal to 0, or vice versa. Both A1, A2 should not be equal to 0. This type of boundary value problem is called Sturm-Liouville problem or a system. Now we will go for example 1. We will just see, look at the equation d squared y by dx squared plus lambda y equals 0, and also just look at the boundary conditions. Y of 0 which is equal to 0, y of pi equals 0. Now this is a boundary value problem, but we know that Sturm-Liouville theorem differential equation is given by this equation. We know already. Now you compare this equation with this equation. Compare equation 3 with Sturm-Liouville differential equation. It clearly says that p of x equals 1. See here, we can have p of x equal to 1. And what of q of x? There is no q of x in equation 3. So q of x equals 0. What of your r of x? That will be equal to 1. So when you are going to compare this boundary value problem of example 1 with Sturm-Liouville differential equation, it clearly says that this equation can be written as exactly like this. So as I said earlier, your p of x equals 1, q of x equal to 0, and r of x equal to 1. So this is a Sturm-Liouville problem. And example 2, also another boundary value problem, dy by dx, x dy by dx plus 2x square plus lambda x cube times y equals 0. So this is equation 4. What are the boundary conditions? They are 3y of 1 plus 4 times y dash of 1 which is equal to 0, and 5y of 2 minus 3y prime 2 of 2 equals 0. So these are all boundary conditions. And when you are going to look at the boundary conditions earlier, see here already we know boundary conditions equation 2. You can compare this boundary condition with this new boundary condition. We can say that A1 equals 3, A2 equals 4, B1 equals 5, B2 equals minus 3. And this is also your Sturm-Liouville problem, Sturm-Liouville differential equation. When you are going to compare this one equation 4 with the Sturm-Liouville equation, exactly it resembles. So this is also a Sturm-Liouville differential equation. Now we will solve example 3. You are going to find a non-trivial solution of the Sturm-Liouville problem. So we are going to find out, our aim is to find out non-trivial solution. The meaning of trivial solution and non-trivial is as follows. It's very simple. Suppose if solution is 0, in a differential equation, here the solution is nothing but y. So you look at the equation 5, we are going to find out only y. So y is a solution. Suppose if y is a solution, this is called a trivial solution. If y is not equal to 0, then we say that it's a non-trivial solution. So for the problem, we are going to find out a non-trivial solution. And the boundary conditions are given as y of 0 equals 0, y of pi equals 0. So this is equation 6. What is the solution? There are 3 cases. So we can have, one is lambda equals 0, lambda less than 0, and lambda greater than 0. And we are going to find out a non-trivial solution of Sturm-Liouville equation, given equation for these 3 cases. We'll find out case 1. So lambda equals 0. So look at the equation 5. Substituting lambda equals 0, we have d squared y by dx squared equals 0. The general solution of this equation is given by y of x equals c1 plus c2 times x. You just substitute the boundary conditions. What are the boundary conditions? Here it is given as y of 0 which is equal to 0, y of pi equals 0 according to equation 6. So your x equal to 0 and x equal to pi. You substitute in this equation, x equal to 0, you substitute here, we will have y of 0 which is equal to 0, which is equal to c1 plus c2 times 0. So it clearly says that c1 equal to 0. It clearly says that because c2 equals multiplied by 0, that will give us 0. So c1 equal to 0. You go for the second boundary condition, x equal to pi. X equal to pi, substituting, that will give you y times of pi which is equal to 0. So we have c1 plus c2 times of pi. Correct. So already we know that c1 equals 0 there. So c2 pi equals 0. It clearly said pi cannot be equal to 0. So only possibility is c2 equal to 0. So in cases c1 and c2 both are equal to 0, So y equal to 0 for all values of x. So it clearly shows the trivial solution, because as I said earlier, y equal to 0 is nothing but a trivial solution for lambda equals 0. So for the first case we have obtained only the trivial solution. Now we will go for case 2, which is lambda is less than 0. The general solution of equation 5. So this is your equation 5, which is given as in a red mark. So this is equation 5. So this equation 5 can be written as auxiliary equation as m squared plus lambda equals 0. The solution of that differential equation is given as y of x equals c1 e power alpha x plus c2 e power minus alpha x. Here alpha is nothing but root of minus lambda. So now again we will have to substitute the boundary conditions, which are nothing but x equals 0. So substituting x equal to 0 in the solution, we have y of 0, which is equal to 0 plus c1 e to the power alpha x. For x equal to 0 we have e power 0. E power 0 is nothing but 1. So we have c1 plus similarly c2 e to the power minus 0. So I can write this as 1 divided by e power 0. So again 1. So c2. So we have 0 equals c1 plus c2. Now x equals pi. You substitute x equal to pi as boundary condition here in the solution of the equation. Then we have y of pi equals 0, which is equal to c1 times e to the power alpha pi. Instead of x we will have to substitute pi, plus c2 times e power minus alpha pi. Now look at the equation, these two equations, c1 plus c2 equals 0, c1 e power alpha pi plus c2 e power minus alpha pi equals 0. So we can find out the values of c1 and c2 by taking the determinant of these two equations. So we will get, taking the determinant of these two equations, we will have 1 e power alpha pi e power minus alpha pi, which is equal to 0. It clearly says that 1 multiplied by e power minus alpha pi minus 1 multiplied by e power alpha pi, which is equal to 0. So we can say that e power alpha pi, which is equal to e power minus alpha pi. So this is equivalent to alpha pi, which is equal to minus alpha pi. So it clearly says that alpha equals 0. So if alpha equals 0, what about lambda? Lambda also equal to 0. If lambda is equal to 0, there are no trivial solutions. See, lambda is 0 here. If lambda equal to 0, again there are no non-trivial solutions. Again this will be only trivial solution. Even for the second case, lambda is less than 0, we have obtained only a trivial solution. Now we will go for the case 3. Our aim is to find out only non-trivial solution for all the three cases using Sturm-Liouville differential equation. So we will go for now general solution of equation 5, which is given by this equation. And what for lambda is greater than 0, the solution is given by y of x equals c1 times sine root of lambda x plus c2 times cos root of lambda x, which is equation 7. Now you substitute x equals 0 as one of the boundary conditions. So y of 0, which is equal to 0, c1 sine 0 plus c2 cos 0, which is equal to 0. Now cos 0, what is cos 0? Value of cos 0, which is equal to 1. What is sine 0? The value of sine 0 is nothing but 0. So it clearly says that c2 plus c1 multiplied by 0 is 0. So c2 multiplied by 1, which is equal to 0, which is nothing but c2 equals 0. I repeat, see here, cos 0 is 1, so we have c2, whereas sin 0 is 0, so this becomes 0, so c2 equals 0. Now we will substitute another boundary condition, which is nothing but x equals pi. So y of pi equals 0, that will give us c1 times sine root of lambda pi plus c2 cos root of lambda pi equals 0. Already we have come to know that c2 equals 0. You substitute here. So substituting c2 equal to 0 in the above equation, we will have c1 sine root of lambda pi equals 0. Look at the equation now. Either c1 equal to 0 or sine root of lambda pi equals 0. Suppose if we substitute c1 equal to 0, already we know that c2, we have obtained c2 equal to 0. Suppose if we are able to obtain c1 equal to 0, then c1 equal to 0, c2 equal to 0, again it will give only trivial solution, which we don't want. We want only a non-trivial solution. For this case, let us try. So we can't set the c1 C1 is not equal to 0. See here, we can't set C1 equal to 0. So C1 should not be equal to 0. Hence, we have to set sine root lambda pi equal to 0, and of course we know that sine n pi equals 0 for all values of n pi we will have 0. So comparing these two conditions, we will have lambda equals n square. So n square, and where n equals 1, 2, 3. So we will have only non-trivial solution, lambda equals n square. So substituting in this equation complete solution, we have y of x which is equal to Cn times sin nx. Of course C2 equal to 0. So instead of C1 we have written Cn. N goes from 1 to 3. So y of x which is equal to Cn sin n of x is a non-trivial solution for this case lambda greater than 0. So that is the end of Sturm-Liouville theory. And of course we know that Sturm-Liouville differential equation is a main differential equation, and whatever we have learnt so far, Hermite differential equation and Legendre differential equation, they are the special cases of Sturm-Liouville differential equation. So that is the end. We will see in the next class. Thank you students. Bye.